occasion of second winter Arab School for Astrophysics. That's held actually for the second time in Morocco. And among us, many scientists actually came to teach in this school. And among us also some students, either from all over the Arab world. We have 30 students, graduate students who attend this school. Welcome all to the school, and welcome all to this series of public lectures. We thought actually, since we have those eminent professors, why not benefiting our community from their knowledge. So our first lecture will be presented by Professor Raed Suleiman. So briefly, Raed Suleiman is a physicist at the Harvard Smithsonian Center for Astrophysics. He's working in the atomic and molecular physics division and the solar, stellar, and planetary science division. Raed is serving on the Center for Astrophysics, Computation Facility, Scientific Advisory Committee. Raed is the PI and the chair of the Scientific Organizing Committee of the Arab Winter Second School for Astrophysics, the school I told you about. Both the International Astronomical Union and the Office for Astronomy Development have endorsed this school we are having at EUI. Raed is one of the founders of the Arab Astronomical Society, and we have all the members here with us. Lastly, Raed has participated in tens of international scientific conferences and co-authored over 50 scientific papers. So he'll be talking to us about the physics of black holes, observational evidence, and future observation. So please welcome Professor Raed. It's a pleasure.
Thank you so much, Professor Darmawi. Thank you so much for having me here. I appreciate the opportunity. It's wonderful to be again in Morocco for the second Arab Winter School for Astrophysics. It's a great pleasure to be here. And today, given that there is significant research or development within general relativity to prove that Einstein was right, although he himself, the poor guy, did not think he was right. But the new development and the discovery, or the third time discovery of gravitational waves, which is Professor Zuhair will speak about later on in Khaldun. However, today I'm going to talk to you about black holes. I'm going to try to make it not very technical. You might see one or two equations, forgive me, but it's important to understand where the whole thing comes from. So the first thing I'm going to talk about, a little bit of a basic physics of what a black hole is. There are types of them, and how do they form, and what's the structure of them, and some examples, and I'm going to provide both stellar as well as galactic. For stellar, we'll talk about Cygnus X1, and will show some movies, and I had in mind some equations to talk about, calculate some numbers, but we thought ignore that and let's talk about common questions. What happens if? And so moving on, what is a black hole? Well, if you think about it, a black hole is something that somewhere that the density is so infinite, so high, that nothing escapes. In physics, that there is, well, I'll tell you about it later on, where everything condensed down to a singularity. In physics, there is no such thing as a singularity where everything is zero. It's a mathematical thing, but physicists decide to be smart about it and decide to make, okay, let's call it a singularity. Something so infinite, so small, that it's close to zero, but it's not actually zero. So basically, everything matter around that physical location is gathered inside that singularity. The small point where all of the mass in the area is inside it. Now, obviously, because it's called black, because not even light can escape it, so it's black. So we don't see anything from it, nothing comes out of it. So someone might say, okay, what do you say? There is a black hole, but then you tell it it's in black and nothing comes out of it. But at the same time, you're going to tell me there are evidence for it. And we will talk about how with the evidence that indirect, like the same way we see electricity. We don't see the electron, but the electron goes through the wire, and that's why you get the electricity. So, first, before we go through that, black holes actually, before the word black holes came to exist, have existed in long time. And to give you a brief history of it, back John Mitchell, followed by Laplace, proposed that there must be some kind of big star that is so black that it's actually presence or actually traps light inside it that nothing comes out. So that's back then. And then Albert Einstein in 1915, he wrote his first paper, not his first, but his second paper in relativity, which was about general relativity. And in principle, there are the forces in the universe, before we skip to, and he proposed in the general relativity that there is a black hole, or this theory said so, although himself did not believe so. It sounded so weird to him. And he couldn't think that something like this could exist in nature. So we all know some form of physics we studied in high school, and all of the physics we must know is the Newtonian physics. And the theory of gravity is what we know as the Newtonian gravity. Einstein made the leap of taking that gravity and adding to it geometry, adding to it the space as another dimension with time. And I will tell you about that, and that's where the existence of a black hole don't exist. If you have a very gravitational, very heavy gravitational body, then light must be inside it, trapped or pinpoint. So then in 1918, a young gentleman was serving in World War I, and as he was working and filling the rockets with the weapons, he was solving Einstein field equation. And he solved it for a spherical body, for assuming a spherical geometry. And he came up with the solution that proposed a black hole for that solution, within that solution. And he, thank God, he decided to send the paper for publication in the middle of the war before he got hit by a rocket. But the poor guy survived the war, but died later on with an illness. He was a young man, Schwarzschild. And so most of the solutions, when you talk about a black hole, people think of the Schwarzschild solution of a black hole, where it's a spherical black hole. There are other black holes, and I will tell you about them later. Then Chandrasekhar speculated the same thing. He, back in the 30s, came back and said, okay, now again, this is based on theory of gravity. General relativity is nothing but a theory for gravity involving the cosmos. And came up and said, okay, the larger stars, they might have not a faint similar, they might not die the same way the younger stars die by just cooling down. And I will show you how black holes develop. But they might actually convert to another star that will lead to black hole, like neutron star. Then in 1963, now Einstein field equation, if you think about it, is very advanced, not the simple partial differential equation, but more advanced than that. But it's a partial differential equation that could have multiple solutions. And Roy Kerr, proposed another solution, solved on the equations, and he came up with that, okay, if I have this solution, I will end up with the rotating black hole. So now we have two black holes. We have a spherical black hole, and we have another black hole that also could be spherical and rotating, or spherical and not rotating. Then, back in '67, John Wheeler, an American physicist, he came back and said, okay, let's coin this. Who came up with this? He happened, although other people, starting with Mitchell and Laplace, mentioned the concept of a black hole, but the word black hole did not exist in our vocabulary until 67, until Wheeler decided to say, hey, let's call this thing a black hole. Now, Hawking in the 70s provided another piece to the puzzle and saying there is radiation from black holes. One can think, okay, how is that? One of the fundamental issues that is still unsolved in physics is, as I said, general relativity is a theory of gravity. However, we still have another theory in smaller objects. We don't think of it too much, but it's very important, quantum physics. And they must work together in order for us to understand and explain the forces in the universe. So there is one way. Well, matter doesn't disappear basically, and information cannot go away, and we still need a theory that's called quantum gravity. And right now there are a few theories of quantum gravity. None of them are solid theory as general relativity is. But general relativity is not complete. We still need to add quantum gravity to the forces to explain the four fundamental forces of the universe. We have electricity and magnetism, which Maxwell added together as E&M. We have nuclear weak, we have nuclear strong, and we have gravity. We need to add gravity with the quantum in order for us to unify all of the forces and understand everything. So, as part of implying or as part of adding quantum effects into general relativity, Hawking came up with what's called Hawking radiation, or what I will refer to it at the end, evaporation of a black holes. Now, what is a black hole? We said, or how does it come to exist? The right answer the right question might be. We told you it's something that's high density in a small location. And if you look at this, that shows you here the cycle of a star, how a star is born and how it could end up to be a black hole. So we start with the star-forming nebula, which what we know, and we know this. So it produces a star, sun like our star. Sun like our star eventually will reach its point of being red giant, eventually in a planetary nebula, and it dies away and goes to white dwarf. White dwarf by itself will not give you black hole. Not there. What will happen so that the star-forming nebula will give you a star like our sun, meaning the same size and so on, and a class. Or will give you massive star, and that's the important one. The massive star will become red supergiant. That thing will explode in a supernova down the road. That could end up to a neutron star and a black hole, and that's what the black hole is. Now, so this is how a black hole is formed. Most of the black holes that do exist tend to have masses greater than that of the sun. It should be in principle of above 20. However, there are observations for black holes within the mass of less than 5 or 4. One of the other puzzling things I will tell you about is there are the supermassive black holes that in the center of galaxies. However, there is nothing in them in between. There should be, but we haven't seen any yet. Moving forward, this is the equation. So this is the poor thing Rothschild was playing with while he was filling the rockets in the middle of World War I. I'm not going to go through it, but one of the, as I said, the leap that Einstein took from Newton is adding geometry to the whole factor. Now, when you study this, you will see there is a flat space. That's the space we deal with here. And there is a curved space. Curved space where there's high gravitational fields and it gets affected with the space around it. So now, solving this equation can give you multiple solutions. And these solutions where you get the black holes, variations of it. There are 4 or 5 or more solutions. I'm not going to go through them. Now, to make you understand and why Rothschild came up with the conclusion for the spherical matter, the spherical object, that there's a black hole and everything cannot escape. If you take just simple physics, high school physics, and you look at your kinetic energy with potential energy and field, you end up with the escape velocity to be this. This escape velocity has nothing to do with the body that's trying to escape the object. It depends on two things. It depends on the radius of the object, the mass of the object, the gravitational constant that Newton came up with. So what that tells us, if I have a bulk or a rocket, it must have one speed, that's escape speed, to leave Earth. Has nothing to do with this mass. And that speed, based on this equation, you can calculate it for any object. In this case, for Earth, it's 11.2 kilometers per second. So if you want to take a cat, unfortunately I like cats, or fortunately, so we are not going to take a cat. Let's take a cow. And you want to launch a cow to escape Earth orbit, you must have the poor cow traveling by 11.2 kilometers per second in order for it to escape Earth. Now, how did that lead to a black hole? So, as I said, Charles Child decided, okay, when he solved this, he came up with the same thing. Look at this. This is, oops, I didn't want to do this. So I go back here. Oh. So we go back here. See this thing? I make this square. This is the square root goes. Bring the R here, bring the thing here. This is exactly his solution here. See it? Except he changed V, which is the velocity, to C. And the guy, when he solved it, realized, okay, in order for anything to escape that spherical object, that's a solution of that equation, this velocity must be greater than the speed of light. Therefore, it cannot escape. And here it shows you that here is a black hole, this is the singularity, and there is the radius. There is a radius based on this. You calculate this radius. Based on this radius, you can determine how far you have to be in order for you, not you, the cow, once it escaped Earth, not to fall inside a black hole. Now, I did some calculations based on this, and everyone can do it. If you take any object, let's say I took an object for 3 solar, the mass of it is 3 times the mass of our sun, then R is 9 kilometers. So what that means, if we took a sun 3 times our sun, squeezed it into 9 kilometers, that's a black hole. Anything below the 9 kilometers is in, anything outside it is out. Now, and I did the same thing for different masses. I did for Earth mass is 9 millimeters. It's close to a bug or something like that. And you can do the same thing for different planets within the solar system. Now I have a question for you guys, although it's not a question time, but let's say we take the sun and the sun transfer into a black hole. What do you think will happen to us?
We're going to be judged.
We're going to be what? We're going to be in a freeze. Nothing is going to happen to us. We're going to fall inside the black hole. Guess what? Because it's 9 kilometers the event horizon. I'm sorry, one mass, 3 kilometers. We are far from, the Earth will maintain its orbit, which is farther from 3 kilometers. The only thing, life won't exist because there will be no light, no nothing. But we will not fall inside a black hole because we are outside this radius. See what I'm saying? So, as I said, black holes based on the mass are 3 of them in terms of classifications. In terms of rotation and in terms of others, there are 3 kinds, and I haven't come to it, but we'll come to it again. We have the spherical, we have rotational. And there's another solution that added one more physical component. And all those, only the 3 physical components you can get out of any black hole. So we have the stellar mass black holes, and as I said, those basically supposed to be within 20 times the size of our sun. The ones that we have, Cygnus X1 is about 14. And they're supermassive, and those tend to be in the center of every galaxy. And there is something that's microscopic, that's all still theoretical. That's when you read sometimes in a newspaper or in a magazine or some science fiction things, it's in Geneva, and someone is going to do something, it's going to create a micro black holes and going to swallow the whole thing. It's not just going to swallow the whole thing, because you're going to have to be inside the stupid event horizon. But the idea here is it's very high density in a small piece that's in a small scale. Those are still theoretical. Now, in here I put the objects that we have already established as evidence of a black holes. This is in stellar black holes, on the meaning masses, and I show you here the mass in solar units, meaning this is 16 times the solar, what do you call it, the 16 times, it's actually 14, I don't know why they say 16, but it's maybe rounding it off. So, to the 16 times the mass of the sun and so on, and they see they are within less than 20. I'm going to show you results from this. Then there is the galactic, which is more based in a larger, supermassive black holes, which is, if you see, look at this, 93 million times that of the sun. One of the things that there haven't been an evidence of, although it should exist, is the ones in terms of hundreds of a solar, of a mass of the sun. We haven't seen those yet. I am supposed to give this in Arabic and English, so there is variation of some Arabic here, so ignore it. Another solution, I didn't want to go through it earlier, but I thought we'll introduce it here, is there was another solution that introduced another physical quantity, which is angular momentum. So now you have, for black holes, you can have spherical, and you get basically the mass you can get from it, a solution, you can get the charge of a black hole, and you can get the spin. So those only the 3 quantities that we know from black holes. That's the 3 physical measurements that we can derive from black holes. Now, most of the results I'm going to show you is based on Chandra X-ray. It's named after the Chandrasekhar in 1930 who proposed that, or who speculated that stars can actually die transfer into neutron stars. That's the massive ones, not the small mass ones. So Chandra is one of NASA's great observatories, as it is, it's X-ray, so it works in the X-ray regime. And it looks at most any sources within our system. It was launched in '99. It has been operating. It's in the same center where I am. We have the the operation center there, and it's one of the things that every time NASA builds something or anyone builds something, you have to build something that in better resolution or can do better measurement that you have done before. So far it has been one of the still working, and it's in better resolution than we had before, prior to it. So I wanted to introduce this here quickly, because I don't want to go over it. I might even skip over it. Hawking radiation. As I said, it's what happened is the black hole, in order for nothing to go in, what comes out, it starts leaking some of the material slowly out from the black hole. However, eventually the black hole is not going to just disappear. It's at some point it will shrink. The mass of it will shrink as more radiation go out and the density. But still, one of the issues behind it is to try to understand how quantum effect would work within inside a gravitational black hole, a heavy body as a gravitational high density like a black hole. So part of this, there are still information, and that's part of why Hawking radiation was proposed as a mechanism. Is, for example, what happens to the information once it goes through the black hole. Again, as I said, once everything goes through the event horizon, we don't know anything. We can't answer the question what happened to the information because we are not getting anything back to tell us what happened. And obviously what's inside the black hole. And does it go to the other end? Is there a white hole? Is there a wormhole? Those are opening questions, more bearing on the science fiction rather than fundamental physics, because until, quantum gravity valid theory of quantum gravity is accepted, this is still part of speculation. So, detections of black holes. So in here, one of the things I said, okay, so black holes, they are black holes. How do they detect them if they are black holes? The black holes, they tend to have a component, accrete material from the surrounding objects. As the material comes in, before it heats up, before it goes into the event horizon, high temperature, it heats up, it produces X-rays, and that's the X-rays we discover. And in here, what I have, this one is both from Chandra, and this is the one is the Saragas A1A, and I will show you later on. And the reason there is a black hole there, as you look at the picture, you realize with the X-rays, there is all of the material, as you can see here, it looks like it's orbiting something dark. But obviously, the dark implies, when you orbit something, there's heavy gravitational thing around you that makes you going around it. So the other observational evidence is Cygnus X1, which is, as I said, was discovered by Uhura satellite back in '74. It's about 14 solar radius, and it's about 60, or I think about 70 light years away from us, 6,000 or something, 70 light years away from us, and this is based on a new measurement by the FABA radio satellites. And in here, this is what I'm showing you, so you know that it's a variable star, and it has an X-ray source. Now you can see this is the done. So you can see the black hole, and it sucks material out. As the accretion of the material around it, it heats up, goes around, it heats up, and jets of X-rays comes out. That's what you will see. You see the X-ray coming out. That's an evidence of the accretion of the material, and you look at it and you see these matter coming around in a dark spot. This is another picture of Cygnus X1, and this is based in both optical, I believe, and an X-ray. This is an optical in here. Oops. So this is an optical image of Cygnus X1. And next evidence it will have is supernova 1979C. And this is made of multiple data, not just one. One of the things that Zuhair hopefully will tell you about when we talk about gravitational waves is sometimes you use different wavelengths. As you can see, we observe light based on the electromagnetic spectrum. So you can see things in X-ray, gamma rays, infrared, microwave, and so on, and radio. And in here, we have a very large telescope for the AWSA's radio, the optical data, and we have infrared from Spitzer. It's one of the great observatories that they are in the red are the Spitzers. And